Hi, Bobcats. In this section, we're going to wind up our discussion of acids and bases by looking a little bit more closely at Lewis acids and bases. If you think back to when we were first looking at Bronsted-Lowry acids and bases, the Bronsted-Lowry definition allowed us to expand the idea of bases to compounds that didn't include hydroxide ions. With the Bronsted-Lowry definition, we could include things like ammonia as being a base because it could accept a proton. Well, with the Lewis definition, we're going to be able to expand what we consider to be an acid and a base, really expanding what we consider to be an acid, because an acid does not have to just have hydrogen ions or be a proton donor. It could be any sort of a substance that can accept an electron lone pair. This opens up a whole new world of compounds that we could consider to be acids. Our objective is to extend the definitions of acids and bases to include reactions that do not involve hydrogen ions, and so this will be the Lewis acids. So the Lewis acid and base definition is all focused on electrons, just like Lewis dot structures are all about electrons. Bases are going to be electron pair donors, and that lines up pretty well with the Bronsted-Lowry definition because the electron pair donor is a very good proton acceptor. But acids now can be something very different. Acids are going to be electron pair acceptors. And so this expands the idea of an acid to include any sort of a substance that can accept an electron pair. And so Lewis acids don't have to contain hydrogen ion. Metal ions like Fe+3 are able to accept a lone pair, and so they will be able to function as acids using this definition. This is an example of a reaction between a Lewis acid and a Lewis base. The Bf3 acts as a Lewis acid because that boron is short of an octet, and so the lone pair on the nitrogen and ammonia can be donated to the boron, and we end up forming a covalent bond between boron and nitrogen based on that donated pair of electrons. That is a little bit different than how we normally think about covalent bonds being formed. Usually we think about each atom in the bond contributing one electron to that bond, but in this case, nitrogen brought both of those electrons in the shared pair. When one atom brings both electrons, it's referred to as a coordinate covalent bond. And this resulting structure here is referred to as a Lewis adduct. The chemistry of transition metals is filled with all sorts of really interesting colors, and a huge part of that colorful aspect of T-metal chemistry is the formation of these coordination complexes, where the transition metal acts as a Lewis acid, and then some sort of a substance acts as a ligand. So a ligand is the substance that will be donating that electron pair, so it'll be some sort of a Lewis base. And the ligands often surround that central atom. Often it'll be either 4 ligands or 6 ligands. The number of ligands that attach is referred to as the coordination number. And as the ligands change, the energy levels of the d electron orbitals on the central metal atom will change. And as those energy levels change and the transition metal absorbs a photon as light illuminates it, the color of the transition metal will change. So if you look at these transition metal complexes, they often will be within a family of colors. Like a lot of the copper transition metal complexes will be either blue or green, depending on the exact nature of the ligands that are involved. So changing that ligand changes the electron energy levels, and so that changes the color of the photons that are absorbed. Down here at the bottom, we're showing these different chemicals. We've got water and ammonia, the chloride ion, and the cyanide ion. These are all compounds that can act as ligands because they have lots of electron pairs on them. Water has 2 of them, ammonia has 1, chloride has several, and then cyanide's kind of interesting because it can attach at the carbon or it can attach at the nitrogen. Iron +3 is a good example of a substance that will change color depending on the nature of the ligands that are attached to it. So if iron has 6 waters attached to it, it'll have this yellow color that we see on the left-hand side. But if you change out one of those water ligands for thiocyanide, it will change color to be this pretty red color instead that we're seeing over here on the right-hand side. If you are taking the 1142 lab, the equilibrium constant experiment involves the formation of this complex ion, and so you'll get to see this nice red color. In this example, we're asked to classify each substance as a Lewis acid, a Lewis base, or neither. Fe+3 is clearly missing some electrons since it has that +3 charge, which means it can be an electron pair acceptor, making this a Lewis acid. CH4, well, I'm going to draw the Lewis structure of that up here. CH4 has a central carbon atom surrounded by 4 hydrogens, and the carbon atom is completely full. It has its octet satisfied. The hydrogens all have their duet satisfied. There are no lone pairs on here. So this molecule will be neither a Lewis acid nor a Lewis base. There's no spot for it to accept an electron pair, and it has no electron pair to donate. Chloride, on the other hand, has an octet of electrons, and the chlorine atom only has 7 valence electrons, but that -1 charge tells us it's picked up 1 extra, so it has that octet. So this can operate as a Lewis base because it has lots of electron pairs that it can donate. Ammonia, if you look at its Lewis dot structure, there is a lone pair on that central nitrogen atom, so it can donate that lone pair, making it a Lewis base. The molecule hydrogen has 2 hydrogen atoms sharing a pair of electrons. They can't really accept any more electrons because each hydrogen only needs 2, and they don't have an extra lone pair to donate. So H2 will be neither. And then iron, just the neutral atom iron will probably act as neither. Now it shouldn't be too hard to oxidize iron, so if you have anything going on in your system that will oxidize iron, then you can turn it into a Lewis acid. This thought question came up in an earlier video, but I'd like to revisit it, and I've added 2 more substances at the very end here. These 2 added substances are both salts. Now what we were asked to do was to rank equimolar solutions of these chemicals from the lowest pH to the highest pH. So lowest pH would mean the most acidic. Can't draw an H anymore. There we go. So lowest pH will be the most acidic, so that'll have the most hydrogen ion. The highest pH will be the most basic. So we'll have the most hydroxide ions present in that. So when we went through into this before, we said, okay, water is neutral, so we'll put that right in the middle with a pH of 7. Ammonia is a weak base. Barium hydroxide is a strong base, but notice it has these 2 hydroxides, so we get double the bang for our buck when barium hydroxide dissolves. HCl is a strong acid. NaOH is a strong base, but it only gives us 1 hydroxide compared to barium hydroxide giving us 2. And then HF is a weak acid. So that leaves us sodium fluoride and ammonium chloride. Well, for sodium fluoride, sodium came from the strong base sodium, and fluoride came from the weak acid hydrofluoric acid. So the strong one tells us what the pH is. So this is going to be a basic salt since sodium hydroxide is strong. Ammonium chloride came from the weak base ammonia and the strong acid hydrochloric acid, so the strong one points us in the direction of its pH. So this will be an acidic salt. And there you thought BS only stood for bad science. It also stands for baking soda and basic salt. Okay, so let's rank these from the lowest pH to the highest pH. The lowest pH is going to be our strong acid, HCl, because that'll fully ionize, giving us the most H plus ions. That'll be followed by our weak acid, HF. Only roughly 1% of that will ionize. So instead of getting a full 0.1 molar H plus, we'll get like 0.01 or 0.001 molar H ions. Then next we'll have our acidic salt, which will be the ammonium chloride. Once that ammonium ion sets up that equilibrium, it will generate a little bit of hydrogen ion. And I believe that took care of everything that's acidic. Let me go ahead and cross those out to make sure we got everything that had an A in it. Okay, so next we'll hit our neutral compound, which is water. I guess I could have put a neutral salt in there as well, something like sodium chloride. It would be right at the same pH as water. Then we have a basic salt coming up next. That would be NaF. The basic salt will be less basic than a weak base. We have the weak base ammonia. Let me go ahead and cross these off as we're writing them out. Basic salt, weak base, we already did neutral. So that leaves us the 2 strong bases. The monobasic base will come next, which is NaOH, and then that highest pH will come with the dibasic base, the one that gives us 2 hydroxides, the barium hydroxide. Our objectives for the entire chapter are listed here. We looked at Arrhenius acids, Bronsted-Lowry acids, and bases, of course, and Lewis acids and bases. We looked at the concept of conjugate pairs. We looked at how water auto-ionizes so that there are always hydrogen and hydroxide ions present if you have water. We figured out how to calculate the pH of a solution. We looked at the equilibria that are established when weak acids and weak bases dissolve in water. And we looked qualitatively at the pH of salt solutions as well as numerically at finding the pH of a salt solution. And then finally, we took a little bit closer look at the Lewis definition to extend our idea of acids to include compounds that do not involve hydrogen ions.